So this is a quick demonstration on how to use the Digital Filter Designer 2024 tool. We will do a quick example to showcase the use of the GUI that comes with the software suite. So let's begin by uh, talking about what is the design requirement of our filter. Let's suppose that we want to design a filter that looks like this. This is the characteristic of the filter. The filter is uh, is basically composed of three bands, as seen in this picture. The first band extends from frequency 0, the DC component, to 500 hertz with a gain of 2. Then, after that, we have a transition of 5 hertz where the filter can do whatever it wants here in this region. It's unspecified. And the second band starts from 500 at 5 hertz and ends at 720 hertz with a gain of 0. So in this area, in the spectrum, we do not need those frequencies. And the last band extends from 730 hertz until 1100 hertz, which is the Nyquist frequency in this case. So in this case, the sampling frequency is double the last frequency in our specified bands, which is, in our case, in the case of this example, 200, 200 and 2000 and 2200 hertz. Okay. So let's translate those specifications to the Digital Filter Designer 2024 GUI. First, we are presented by this form, and we need to input the values we talked about. So first of all, we need 3 bands. Right now we have only 1 band, so I will add another 2. I will start by specifying the lower edge of the first band, which is, of course, 0 hertz. And after that, the upper edge of the first band is 500 hertz. The total gain in this band is 2, and I will give it a weight of 1, which is a default weight. And sorry, I typed 5000. It's 500. After that, in the second band, it starts at 500 at 5 and ends at 720 hertz. And the gain in this band is 0. I will give it a weight of 2, just to say that the second band is slightly more important than the first band, because those frequencies I want to attenuate as much as possible to get rid of them. And after that, we leave a gap of 10 hertz for the transition band between 720 and 730, which is the start of the third band. We can see here. And it ends at 1100 hertz with a gain of, I think it's 1.6. Yes, it's 1.6. And also I will give it a default weight of 1. Right now, I chose the filter length to be 100. Of course, this is a type 2 filter, so it will become 101. So I will put 101. And I can, before plotting, saving, or generating the code or anything, I can just click on the check button and see the delay caused by this filter, which is only dependent on the sampling frequency, which is 2200 hertz in our case, which is double the Nyquist frequency or the maximum frequency of our filter. And we can check this health score. Right now it says below average. Let's see why, before adjusting the length or making the transition bands smaller. We will see why this filter has a below average score. So right now 3 plots will open when I click on the plot button. The first one in green, just wait a few seconds. The first one in green is the impulse response. This is the time domain impulse response of the filter, and those are the coefficients. Those are the 101 specified coefficients. So it's not very important to check this plot. The second plot is the plot of the amplitude response. So this is the frequency domain response, but in decibel. So it's logarithmic. Nothing to look at. If we look at the amplitude response linear, which clearly shows a gain of about 2 between 0 and let's say 484. What did we say in our specification? We said that we want to start at 500. So okay. And then we see here an attenuation. If we go back to there, of minus about 17 decibel, which is not that big of an attenuation. And then we have about 1.6, as we specified, gain in the third band, but there is too much ripple. Okay, so this is why I will close those plots and go back to the GUI. This is why the score is below average. So let's improve that by increasing the filter length. Let's say I want 601. I increase the filter length and I check again. So right now the health is at its best. This is the best possible score to get. Now, you can't rely too much on this parameter, but it really helps before plotting and checking the plots. So if it's in green, it's 90% possible that the filter is good. Let's plot and see what's the difference between the below average and now the filter with best score. Again, the first plot in green is the impulse response. We won't look at it because there's not too much to extract from that. Right now, it's a little bit slow because I'm turning on my screen record and stuff. So let's close this one and check the linear amplitude response. Right now, it looks much better. The ripple is smaller, and for sure the attenuation is higher, about 30 dB or something. Okay, so way better than the minus 16 dB. So okay, for the sake of continuing the example, I will suppose that this is the filter I want. So first thing to do, we need to save the coefficients. The software will ask for a path. I will save it here. So the coefficients are saved. The file name is coefficients.csv. I can go and check those coefficients. They are in double precision format. I think they are here. So those are the 601 coefficients the GUI created. Okay, nothing to do here. So another thing we can do is to generate a MATLAB code. Also, we need to specify a directory. I will select the same directory called MATLAB. Now we can use the MATLAB code to also analyze the filter. This is the MATLAB code. You can check it and run it. I won't go into the details of this. For sure, you know MATLAB, and that's not mandatory. So this was a demonstration of the whole code. What else do we have? We saw the check, the plot, save, code. Okay, great. So that's it. Make sure to check out the extensive documentation on the GitHub repository and to start the repository if you think this software is important. And thank you.